Continuity and one-sided limits. In the past couple lessons, limits were evaluated from both sides of a C value. In this lesson, limits will be evaluated from only one side of a C value. These are called one-sided limits. This really helps with the understanding of continuity and allows for a better and more mathematical definition instead of the informal definition below. Now, the informal definition of continuity that most students encounter throughout their mathematical career is if you look at the graph, a graph is continuous if you do not have to lift your pencil as you trace the graph from left to right. So another example might be something like this. You all know the absolute value function. As you trace this blue graph from left to right, that is a continuous function. A function that is not continuous, by the old definition, would be something like this. This is a piecewise function that does not meet up at the same y value when x is -1. So we will take a look at some examples of continuity or discontinuity and how to classify these different discontinuities. Before we take a look at continuity, it is a good idea to first understand what one-sided limits are. One-sided limit is defined as the following. Here you can see there are two versions of one-sided limits. This first version we have the limit as x approaches c from the left. That's what this negative exponent means, of f of x. In red, we have the limit as x approaches c from the right. That's what this plus sign means, of f of x. And you've seen this before when we were estimating limits graphically. We had to find out which y value the function was approaching from the left and from the right. And the question that was eventually asked was, is the function approaching the same y value from the left and from the right? That question that was being asked is summed up in this statement. If the limit as x approaches c from the left of f of x is L, and the limit as x approaches c from the right of f of x is L, then the limit exists and is L. So you've had an idea of what left and right-sided limits are, but now this is a more formal way of writing out what they mean and how they relate to finding a two-sided limit. One other thing I want to make clear up here is just a little bit more vocabulary. I said it, but I didn't write it. This negative, when you see that negative as the exponent, we could also call this a left-sided limit. And here we could also call this a right-sided limit. Use the graph to calculate each limit. The first limit is the limit as x approaches -2 from the left of f of x. F of x is graphed here at the right. So as we are traveling along from the left side of -2, it looks like the y values are approaching -2. So the limit as x approaches -2 from the left is -2. The next limit, the limit as x approaches -2 from the right of f of x, that'll be up here. As the function approaches -2 from the right, the y values are approaching +4. So that's it. The limit as x approaches -2 from the right of f of x is 4. And this last limit, the limit as x approaches -2 of f of x, that is from the left and from the right. So you can see over here with the graph that as the function approaches -2 from the left, the y values are approaching -2, just like we said over here. As the function approaches -2 from the right, the y values are approaching +4. These two numbers are not the same. So the limit as x approaches -2 of f of x does not exist, just like what you've learned already in the previous lessons. Now, with these other three limits down here, we will be looking what happens with the function at x equals 2. So in the first limit, as x approaches 2 from the right, we will come over here to the graph and approach 2 from the right. So what that looks like then is it looks like the y values are approaching a +3. So the limit as x approaches 2 from the right of f of x is 3. The next limit, the limit here is x approaches 2 from the left of f of x. That looks like this on the graph. The limit as x approaches 2 from the left, it looks like that function is also approaching a y value of 3. So in this last limit over here, the limit as x approaches 2 of f of x, that's from the left and from the right, we can even just look here. As x approaches 2 from the right, it's 3. As x approaches 2 from the left, it's 3. Since those numbers match, the limit is 3 on both sides. And you can tell that that's the case from your previous knowledge of looking at limits on a graph. Now these ideas that the limit approaching an x value and the two-sided limit not existing or the two-sided limit existing, you will see again in about 10 minutes. Calculate each limit. The purpose in showing you these three examples is to get across that finding one-sided limits analytically is exactly the same as finding two-sided limits analytically. That being said, your first move should be to directly substitute into the function and see if it works. So here, the very first thing we will do is when we're trying to find the limit as x approaches 2 from the right of this function is directly substitute the 2 in. And when you do that, you'll get a function that looks like this. 2 minus 3 over 2 plus 2. So you can simplify the numerator and denominator to get -1 over 4. Okay, direct substitution worked. Even though we had a one-sided limit, we are still allowed to use the same techniques to find these limits. In the next example, we have the limit as x approaches -7 from the right of the absolute value of x plus 7 over 3x plus 1. So again, we want to try direct substitution here. Substitute this -7 in for x, and you'll get something that looks like this. -7 plus 7 inside the absolute values, all over 3 times -7 plus 1. So when you simplify the numerator, you end up with 0, and in the denominator, you end up with -20. 3 times -7 is -21, plus 1 is -20. And that is simply 0. And in this last example, we should always try substituting the 6 in for x first. But in this case, when you do that, you end up with a 0 over 0. And hopefully, in this example, you can see that you will need to use the LCD technique to actually calculate this limit. And when you use the LCD technique, you should get an answer 1 over 18. I'm going to let you work through this limit to see if you can get the answer 1 over 18. Calculate each limit. Most of the examples you'll see on the next two slides are one-sided limits. So let's take a look at this first one. The limit as x approaches 2 from the left of f of x, where f of x is this piecewise function. Our clue here as to which function we should know to use can be found here. We want to know the limit as 2 approaches x from the left. We can use that to find out which domain we will be in. So x is less than 2 means that this graph exists to the left of 2. So we will use this top function here. So I can rewrite this limit. The limit as x approaches 2 from the left of x cubed minus 3. And now a direct substitution can be made, leaving you with 2 cubed minus 3, which is 5. So that limit as x approaches 2 from the left of f of x is 5. In this next limit, we have the limit as x approaches 3 of f of x. And in this example, f of x is the same function we used for number 1. So looking at this limit, we don't know which function to use, but we have a clue here as x approaches 3. Once we figure out where 3 is, or which domain contains 3, we will know which function to use. So 3 is bigger than or equal to 2. So here, with the bigger than or equal to 2, f of x will be the function 3x plus 7. So it can be rewritten as the limit as x approaches 3 of 3x plus 7. A direct substitution can be made, leaving the expression looking something like this. We have 3 times 3 plus 7 when that direct substitution gets made in here. 3 times 3 is 9 plus 7 is 16. So the limit as x approaches 3 of f of x, we had to find out which function to use, and it ended up being the bottom function, is 16. In this last example here, the limit as x approaches 3 from the left of the absolute value of x minus 3 over 2x minus 6. And this is the first time I am showing you an absolute value function in a limit. It might be wise to see what form this takes if we try to directly substitute this 3 in for x. If a direct substitution is made, the result will be 0 over 0. This should alert you that the original function can be simplified. But how? This is where keeping in mind the absolute value function can be piecewise defined will help us out. Any absolute value function can be defined in the following way. You set the absolute value portion equal to the positive version of what's on the inside and the negative version of what's on the inside. Then there's this little detail about knowing where the domains are. So this absolute value function will be positive if x is greater than or equal to 3. It will be negative if x is less than 3. How do you find out what number goes here? This number is what makes the absolute value 0. Armed with this knowledge, we are now in a similar situation as in example 1. So this function can be rewritten as the limit as x approaches 3 from the left. From the left is what's going to help us pick which function to use, the top or bottom function over here. And since the function is approaching 3 from the left, that means the x values will be less than 3. So we are looking for this function here. So the function will be rewritten like this. So there's still some simplification that needs to happen. It looks like a 2 can be common factored out of the denominator, leaving you with a limit that looks like this. And now hopefully you see that the x minus 3's reduce away, and that leaves you with a final answer of -1/2. Continuity. The graph of a continuous function has no breaks, gaps, or jumps. This is another way to say what was stated on the first slide, that you can trace the graph of a continuous function without lifting your pencil. Now we will take a look at what makes a function continuous using limits. Over on this side of the page in red now, we have a definition for the continuity at a specific x value, c. The first thing that needs to happen in order for a function to be continuous at x equals c, one specific point, is that f of c must exist. The second thing that must happen is that the limit as x approaches c of f of x must exist. The last thing that needs to happen is that when you take the limit as x approaches c of f of x, it must be the same thing as if you evaluate the function at c. And we will generalize this a little bit on the next slide. Theorems about continuity. You can see there are 3 theories about continuity, and I want to mention this one down here first. That is, all polynomials, all rational functions, and all 6 trig functions are continuous at every point in their domains. And this takes a lot of work away from you in checking whether or not a function is continuous at a given point, which you would have to check all 3 conditions on the previous slide. Now, with this first theorem up here, if you have 2 functions that are continuous, f and g, at a single point, x equals c, then any combination of these functions, if you add them, subtract them, multiply them, or divide them, as long as the limit as x approaches c of g of x is not 0, all of these functions are continuous as well. And with this last theory here, if g is continuous at a specific x value c, and f is continuous at g of c, then f composed g is continuous at x equals c. The other way to say that is the composition of continuous functions is a continuous function. So these 3 theorems about continuity will help when determining whether or not a function is continuous. With all of that on the previous slide having been said, functions can be discontinuous in places, especially with that last theorem on the last slide, theorem 3. Polynomials and rational functions and all 6 trig functions are continuous on their domain. Rational functions may have vertical asymptotes. Trig functions may have vertical asymptotes. Polynomials or all sorts of functions could have holes in the graph. So we will need to be able to locate where these discontinuities are. And before we get into locating these, you should understand that there are 2 different types of discontinuities. We will classify discontinuities as either being a removable discontinuity or a non-removable discontinuity. Now, removable discontinuities you may know by a different name from previous math courses, and that would be a hole. And non-removable discontinuities you may know as vertical asymptotes or jumps in a graph. But this is calculus. We can't just say removable discontinuity is a hole in the graph or non-removable discontinuity is a vertical asymptote or a jump. We want to use limits to help us describe more mathematically what the difference is between these different types of discontinuities. A function has a removable discontinuity at x equals c if the limit exists. Note, this is a two-sided limit, but the two-sided limit of f of x as x approaches c is not equal to f of c, or f of c is undefined. You will see some pictures of what this looks like on the next slide. As for non-removable discontinuities, a non-removable discontinuity at x equals c happens if the limit as x approaches c of f of x does not exist. And we have to dive a little bit deeper into this on the next slide, this does not exist portion. One final thing I would like to mention about these discontinuities is if you go back and look at what makes a function continuous at a particular point c, it needs to have a limit existing, and that's why this removable discontinuity here is a discontinuity. The limit does not exist. The function needs to be defined at that particular x value c. And if you look at the removable discontinuity, f of c is undefined, and that would leave a hole in the graph. And the very last one, the very last property for being continuous was the limit as x approaches c of f of x needs to equal the function evaluated at c. So knowing the 3 properties for continuity at a point really helps with the understanding of the discontinuities at a single point. On this slide, we have an example. Let f be the function whose graph is given. And that's the blue graph over here. Find and classify all discontinuities. Now you might be familiar with where the discontinuities are already located. You can see that there is a vertical asymptote at x equals -7. There's a hole in the graph here at x equals 2. There's another hole in the graph here at x equals 3. And there's a vertical gap here at x equals 5. So you know there are 4 different discontinuities here. Let's classify these. The first discontinuity I would like to look at is this one at x equals 5. So if we look at the limit as x approaches 5 of f of x, This is a two-sided limit we need to look as x approaches from the left and from the right. As the function approaches 5 from the left, the y values are approaching 3. And as the function approaches 3 from the right, the y values are approaching -3. These two numbers are not the same, so this limit does not exist. That means there is a non-removable discontinuity at x equals 5. When we take a look at the next discontinuity right here, this discontinuity at x equals 3, we can take the limit as x approaches 3 from the left and from the right. So let me write that over here. The limit as x approaches 3 of f of x. And in this case, you can see that from the left, the y values are approaching 1, and from the right, the y values are also approaching 1. So the limit here does equal 1. So we put a number to that limit. But there's a hole in this graph. And what we say here is that f of c, in this case 3, is undefined. So that means there is a removable discontinuity at x equals 3. This third discontinuity right here at x equals -2, we have something very similar happening. When we look at the limit as x approaches 2 of f of x, from the left, the y values are getting closer and closer and closer to 5, and from the right, the y values are approaching 5. So again, we can put an answer to the limit here. That's great. One thing that's different between this discontinuity and this discontinuity is that f of -2 is defined, but it's way down here. So we know that the limit as x approaches -2 of f of x is 5, but the actual function value of x equals -2 is -5. That's that point right there. So in order for this to be continuous, we need the limit to equal the actual function value, but it does not. So we can write that f of x has a removable discontinuity at x equals -2. And again, that's because this number, the limit, does not equal where the point is actually located. The point is located at -5, the limit happens at +5. Since this point doesn't have the same value as this limit, then we have a removable discontinuity. Now this last one, the limit as x approaches -7. I'm going to write that way over here underneath the graph. The limit as x approaches -7 of f of x. Now you might know that as we travel from the left and from the right, as we approach from the left and from the right, that this left-sided limit goes off to infinity and this right-sided limit also goes off to infinity. So you say to yourself, well, we have a limit that is infinity. However, on the previous slide, I mentioned that there is a non-removable discontinuity if the limit does not exist as x approaches a specific c value. And the definition of does not exist pertains to it not existing, the limit not existing as a real number. Infinity is not a real number. Infinity isn't even a number. It just keeps growing and growing and growing. So the limit as x approaches -7 of f of x equaling infinity means this limit does not exist in the real numbers. And so since this limit does not exist in the real numbers, we can say that there is a non-removable discontinuity at x equals -7. So again, I want to just reiterate that even though you can find an answer to a limit, it needs to exist in the real numbers. Infinity is not a real number. So this limit does not exist in the sense that we can't call it a number. Determine and classify the discontinuities of each function. For the first example, the function is f of x equals x squared minus 2x minus 3 over x squared minus 5x minus 6. The first thing we should do is find out where these discontinuities are. Since we have a polynomial being divided by a polynomial, this is a rational function. It was stated earlier that rational functions are continuous on their domains. I think what we should do first is find out which values of this function are not in the domain. And you can do that by setting the denominator equal to 0 and solving for x. So in this instance, it will be easiest to factor the denominator into x minus 2 times x minus 3 and set each one of those equal to 0, each factor set equal to 0, and solve for x. And so we will get that one of the x values where the function is discontinuous is at x equals 2, and another x value where the function is discontinuous is x equals 3. Now the defining difference between whether a discontinuity is removable or non-removable is what happens when you take the limit at these particular values where discontinuities happen. If the limit of a function as x approaches a discontinuity exists, then that number represents where a removable discontinuity happens. If the limit is taken as x approaches the discontinuity and it does not exist, then the limit will represent a non-removable discontinuity. So we need to check out these limits. Let's see what happens as x approaches 2. When 2 gets directly substituted in for all of these x's, then you will see that you end up with a form that we haven't run into yet, but there is a number other than 0, and in this case it would be -3 over 0. So this tells us, this -3 over the 0, that tells us that this fraction will have a limit that does not exist as x approaches 2. So this limit does not exist. So what that means is that when x equals 2, this is a non-removable discontinuity. Now we can do the same thing for the limit as x approaches 3, and you will see in this case that if you directly substitute 3 in for all of these x's, that you end up getting a 0 over 0, which means this fraction can be simplified. Well, it's staring you right in the face once you have everything in a factored form as the x minus 3's reduce away. And after you reduce the factor of x minus 3 from the numerator and denominator, you will get the limit as x approaches 3 of x plus 1 over x minus 2 is equal to 4, which exists and is a real number. So since the limit exists, but there's a discontinuity at x equals 3, this means there's a removable discontinuity at x equals 3. Now, as we go along and look at more examples, this entire process here gets streamlined. Let's take a look at example 2 to see how that happens. In example 2, we have a function g of x equals x cubed minus 2x squared minus 4x plus 8 all over x squared minus 4. With rational functions only, the first thing you will want to do is factor the numerator and denominator, and that looks like this. So looking at the numerator using factor by grouping, you can group the first two and the last two, factor an x squared from the first two, factor a negative 4 from the last two terms. That's where the x squared minus 4 is, and you're left with an x minus 2 left over. The denominator, x squared minus 4, factors into x plus 2, x minus 2 by difference of squares factoring. Now, the numerator here also factors into x plus 2, x minus 2, but since there are two factors of x minus 2 is squared in the numerator. So the first step for rational functions, polynomial divided by polynomial, factor numerator and denominator. The next step is to set the factors in the denominator equal to 0 and solve for x. The discontinuities for this original function are located at x equals negative 2 and x equals positive 2. The last thing that needs to be done is to come back over here to the factored fraction and simplify it. When we do that, we are able to get rid of the x minus 2, the x plus 2, and 1x minus 2. And let's rewrite that. That becomes x minus 2. Any factor that disappears from the bottom corresponds to a removable discontinuity. So each factor that's here, x plus 2, that corresponds with the x equals negative 2 discontinuity. That factor disappeared when we simplified. That means x equals negative 2 is a removable discontinuity. When you look at the other factor, x minus 2 in the denominator, that also reduced away, which means x equals 2 is a removable discontinuity as well. So the process gets streamlined when you think about factoring a numerator and denominator, finding the discontinuities from the denominator, and then simplifying this fraction. Any factors left over correspond to a non-removable discontinuity, and any factors that disappear from the denominator are corresponding to removable discontinuities. In this next example, h of x equals x minus 1 times x plus 2 over x minus 1 times x plus 2 squared. This is a rational function. If you multiplied all of this out in the numerator and denominator, you would end up with two polynomials. So we can jump right into finding where this function is not continuous. So So we take each factor in the denominator, set it equal to 0, and solve for x, and you will see that there's a discontinuity when x equals -2, and a discontinuity when x equals 1. The next step would be to simplify this fraction as best we can. And you can see that the factors for x minus 1 reduce away. And there's also a factor of x plus 2 that reduces away, but we're still left with an x plus 2 in the denominator. So when all is said and done, this function becomes 1 over x plus 2. And in this simplified fraction, we now do not have this x minus 1 in the denominator. That means x equals 1 is a removable discontinuity. However, there is still an x plus 2 factor in the denominator, which means the discontinuity corresponding to that factor will give you a non-removable discontinuity. In example 4, we have a function k of x equals cosine of x over x plus 2. Now, one thing that you should keep in mind when looking at this is that this function is not a rational function. And that is because there is a cosine in the numerator and not a polynomial. Because this function is not a rational function, you will have to go through and use limits to show whether or not a discontinuity is removable or non-removable. Clearly, this function is not continuous when x equals -2. So what do? We take the limit as x approaches -2 of k of x, which is the same thing as writing the limit as x approaches -2 of cosine of x all over x plus 2. And again, if you try substituting this -2 in for x here and here, you will end up with a value that is not 0. In other words, cosine of -2 over a value that is 0. And what that tells you is that this limit does not exist, which makes the x minus 2, the discontinuity at x equals -2, non-removable. In this next example, we have f of x equals sine squared x over x. And again, we look at the denominator to guide us to where the discontinuities are. And if you set the denominator equal to 0 and solve for x, you will see that the discontinuity is at x equals 0. Now, this is not a rational function. Again, there is a trig function involved in this fraction, so this is not a rational function. We must use limits to see whether or not the discontinuity at x equals 0 is removable or non-removable. So you take the limit as x approaches that discontinuity. The limit as x approaches 0 of sine squared x over x. And if you try substituting this 0 in for x here and here, you'll end up with the indeterminate form 0 over 0. So that means this function can be simplified a little bit so that we are able to find a limit. So this function can be simplified first by separating off one of the sign of x's. From here, this is a special trig limit, this sine of x over x. So that part we know will end up being 1 because the limit has x approaching 0. Also, we know that if 0 is directly substituted in for this sign, that the sine of 0 is 0. So this entire limit is 0 times 1. And 0 times 1 is, in fact, 0, and that is a real number. So we know that there's a discontinuity at x equals 0, but when we find the limit as x approaches that discontinuity, 0, we get a real number. That means x equals 0 is a removable discontinuity. In this last example down here in blue, we have a function, a piecewise function, p of x equals 2x plus 3 if x is less than 1, and x squared plus 4 if x is greater than or equal to 1. And anytime you have a piecewise function, not only do you need to check each function individually for discontinuities that are on the interval specified for that function, but you also need to check where this domain breaks. So there's always a chance that there's a discontinuity at this value. And you have to check by taking the limit from each side of 1. So as you look at the limits as x approaches 1 from the left, that gives you this top function here, because to the left means less than 1. And you substitute 1 in here, you'll get back 5 for your limit. If you look at the other function, this is the limit as x approaches 1 from the right, and that means greater than 1, so we use this bottom function. If you substitute 1 in there, you'll get back 5, which means the limit as x approaches 1 of f of x, that's a p of x, equals 5. So one of the conditions for checking continuity at a single x value was that the limit must exist. And yes, the limit does exist. Another condition that needs to be met is that p of 1 also exists. And yes, it's true that if at x equals 1, there's a function there. The very last thing that we needed to have happen was that the limit as x approaches 1 of p of x must equal p of 1. And that's true. So this function is continuous. That's what we can conclude. P of x is continuous. On this slide, you will be introduced to the idea of continuity on a closed interval and the intermediate value theorem, abbreviated so nicely as the IVT. So continuity on a closed interval looks something like this. You have a graph of a function, but we're only looking at that function on a small interval, not the entire x-axis. And continuity on a closed interval means that at these endpoints, you have closed dots that match up with the old definition of you can draw this graph without lifting up your pencil. So there are no holes in this graph going left to right. And we say that this graph represents a function that is continuous on the closed interval a to b. And I just need to mention this because it is immediately used in the intermediate value theorem. The intermediate value theorem states, if f is a continuous function on the closed interval ab, and k is any number between f of a and f of b, then there exists at least one number c between a and b such that f of c equals k. Luckily, this theorem makes much more sense when you think of it in terms of finding zeros or roots of a polynomial. Intermediate value theorem examples. Use the intermediate value theorem to prove f of x equals x squared minus 5x plus 3 has a zero on the interval 3 to 6. First thing we need to do is answer this question. Is f of x continuous on the closed interval 3 to 6? And the answer is yes, because f of x is a polynomial. The next thing we need to do is find out what are the y values at the endpoints. So we need to find f of a, which is f of 3, here's a, and that is equal to negative 3. We also need to find out what is f of b. F of b equals f of 6, which is 9. So what the intermediate value theorem states is that since we are looking for a zero which has a y-coordinate of 0, is 0, which would be our k, is that between these two numbers? And the answer is yes. So what this means is that since the function is continuous on this closed interval, and the y value we are interested in this case 0, is between the y values of the endpoints, then the intermediate value theorem guarantees, IVT guarantees there is at least one 0 on the interval 3 to 6. Now in pictures, this looks something like the following. We know that the graph we are working with is continuous. So that means when we go from one endpoint to the next endpoint, we cannot lift up our pencil at all. So one endpoint we already know, when the x value is 3, the y value is negative 3. The other endpoint we already figured out, when the x value is 6, the y value is 9. It's about right there. So, if this graph that gets connected between these two endpoints is continuous, that means the graph has to cross the x-axis somewhere. That's what the intermediate value theorem states. If you start on one side of the x-axis and at the other end of the interval you end up on the opposite side of the x-axis, there has to be a 0. There is C. Finding C is a little bit different. Luckily, we will just use the intermediate value theorem to search or prove that there is a 0 on a given interval.